And let's make a couple observations, right? The first integral, okay, it's actually going to go to 0. Why? Well, essentially because f is C2 and phi is integrable at the origin, okay? So actually I can make this part disappear just by knowing that if I differentiate this function twice, I still have a continuous function, right? And I'm taking something that's integrable and I'm shrinking the region over which I'm integrating it down to 0, okay? As epsilon goes to 0, okay? So that the singularity actually is removed with ease. Now, what about the second integral, okay? Well, I'm gonna need something that I'll call Green's second identity, which I will work out for you now, okay? So the divergence theorem implies the following, okay? That if I just have the integral over just the Laplacian of u, this is equal to the surface integral over the normal derivative of u, okay? Another thing I can say is that the integral of this product, this is sort of like multi-dimensional integration by parts, right? Is u dv dn ds minus integral over the volume gradient of u dotted with gradient of v dx, okay? And just taking the mirror image of that, if I integrate this expression by parts, then I get v du dn ds minus integral over gradient of v, gradient of u, dx, okay? So this is what we call Green's first identity, okay? Now to get Green's second identity, I'm just gonna subtract these expressions and I get the integral of u Laplacian v dx minus integral of v Laplacian u dx is equal to the integral over the surface of u dv dn minus v du dn over the surface. So this is Green's second identity, okay? So that in a nutshell is a lot of useful tools for manipulating integrals with Laplacians in them, right? So if we use Green's second identity, right, we can actually take this expression here, right, and unfold it using Green's second identity to now get 3 terms, okay, that it turns out are going to be a bit easier to deal with, okay? So were we okay with that? Do you need more time on this or can I move on? Okay, I want to make sure I'm not whipping through too fast. Okay. So using Green's second, okay, I get the integral over u epsilon phi of y, Laplacian of y, f of x minus y, dy. This is equal to, okay, the integral now over the boundary. So let's look back here. What is the boundary of this domain? U epsilon. Well, there's no boundary as I go out to infinity in either direction. There's no contribution there. The only boundary is the ball here. It's on the surface of the ball, right? But the boundary from U epsilon is going to actually be pointing this way, right? It's going to be pointing into the ball because I'm looking from U epsilon into that singularity, okay? That's important to remember when you're thinking about the convention of the normal derivative, okay? So I have dB 0 epsilon here, okay? And so I have phi of y df dn y x minus y minus f of x minus y d phi dn y of y, and then ds y, okay? All right, and then plus integral over the volume now, which is going to be Laplacian phi of y f of x minus y dy, okay? And so just as a note, right, there's no contribution from bound at x goes to infinity, right? All right, so we can start dealing with all these pieces now. Well, first of all, the second integral vanishes because why? Well, phi is harmonic on U epsilon, right? If I just have phi of y here and I've cut out y equals 0, then it's harmonic everywhere else, okay? Not dealing with phi of x minus y, just phi of y. So that part is gone, okay? The other thing which I remarked on before is that the unit normal ny, okay, is to interior of b of 0 epsilon, right? Let's just draw this little thing here just to remind us b 0 epsilon, right? It's pointing in there. And so that means that ny is equal to minus y over epsilon, right? Which clearly is going to, well, y is going to shrink, right, as epsilon shrinks too, right? So that's not necessarily going to blow up. And d phi dny, you wouldn't expect it to blow up since this is unit normal, okay? So d phi dny of y is equal to minus d phi dr of y, now evaluated at y equals epsilon, which is equal to 1 over n alpha n epsilon to the n minus 1. R is equal to the norm of y. And the integral over this surface now of phi of y df dny x minus y dsy, that's actually going to go to 0 as epsilon goes to 0 because phi is integrable at the origin, right? So as I shrink down this surface integral, right, I'm making it smaller and smaller, that surface integral should shrink down to 0. So the only thing left really should be this term here, right, because of the derivative of phi, right? So now I I'm picking up basically the singularity in phi through its normal derivative. So that means that the Laplacian of u is going to equal the limit as epsilon goes to 0 from above, okay, of minus integral over this ball now of just this last leftover piece, f of x minus y. And now I plug in the value that I got for this term here, which is 1 over n alpha n epsilon to the n minus 1, okay, which is actually equal to that limit, okay, essentially computing the average over this surface, dB 0 epsilon of just f of x minus y, right? Because this is really just dividing by the surface area of the unit sphere, right? So if I'm dividing by the surface area of the unit sphere, and I'm integrating over the surface of, sorry, not the unit sphere, but the epsilon sphere, and I'm integrating over this epsilon sphere or ball, then that's just the average, right? And the average of a function, if I shrink that domain just down to a point, I should get back the value of the function at that point, right? Which the point that I'm shrinking down to is y equals 0. So I'll get f of x minus 0, which is just f of x, right? So I get minus f of x. So that's a little smoosh there, okay? And that works is explicitly because f is continuous, okay? It works because f is continuous. So this implies that minus Laplacian of u is equal to f, okay? Which is what we wanted to prove, okay? So that's why that works as a fundamental solution to Poisson's equation, okay? Questions about this? Okay. It's all right. Well, I don't really see any need to plow ahead. I can maybe wait till next time. And I think next time I'm gonna just do like a warm-up problem. Since we usually work problems on Fridays, but then I'll probably do, I'll then